SwayamPrabha. Digital India. Educated India.
This is one of the most important lecture in this course. Here we are going to provide the stability of the closed loop control system without solving the characteristic equation of the closed loop transfer function. Here we are going to form a table. By inspecting the first column of the table, we can comment on the stability of the system. And also we can comment how many poles are there in the left hand side or right hand side. Here also we are going to find the range of controller gain for which the system will be stable, and also we will find the ultimate gain for which the system will be marginally stable. And then we'll conclude the lecture with some examples. In this lecture, we'll be discussing the stability criterion. Stability criterion. Here, we'll be discussing how we can come up with some conclusion on the range of gains should be considered to maintain the stability of the system. If you consider our PID controlled attitude control system, if you consider PID controlled aircraft attitude control system, suppose we have a step command R of S, and here in the control system, in the control block, let's say we are having PID controller, and we have plant here, plant, this is aircraft attitude motion dynamics, and we are having output. This is the feedback class, and in plant we had 1 upon I s squared, the plant transfer function, and in for the transfer function for PID control we know Kp plus Kds plus Kis. Now, if you want to find the closed loop transfer function CLTF, we are going to have Ys by Rs. Here we have assumed H of S equal to 1 unity feedback. So Gp of S, Gc of S, 1 plus Gp of S, Gc of S. Now, if you substitute the transfer function for the different systems, we are having for plant 1 upon I s square into Kp plus Kds plus Kis, and 1 plus Is square Kp plus Kds plus Ki upon S. And if you simplify this expression, we'll have Kp plus Kds plus Ki by S divided by, we can write Is square plus Kp plus Kds plus Ki by S. If you further simplify this expression, we can get Kds squared plus Kps plus Ki divided by ISS cube plus KD S square plus APS plus KI. So now, if you notice this equation, this is the characteristic equation we are having. This, the numerator, this is basically characteristic equation. And if you notice here, we are having three unknowns. One is KD, KP, and KI. But the previous methods, what we have done, it is difficult if you are going to apply that method here to find these gains. So in this lecture, we'll come up with some conclusion, how we can come up with some range on these gains. And based on that, we can come up with the stability criteria. A system will be stable if you have these values for these gains. So let's consider most of the linear system. First, let's go with the concept linear system. The closed loop transfer function has the following form: y of s r of s equal to a naught s to the power m plus a1 m minus 1 plus dot 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 a m. And sorry, denominator part b naught s to the power n plus b1 n minus 1 plus dot 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 bn. And here, generally, we define the stability of the system based on the characteristic equation or the poles of the closed loop transfer function. Now, based on the B naught, B1 till Bn, the values of these will define the stability of the system. So let me write a note. The poles obtained would be specific to the coefficient Bi. Now, based on this, let's come up with two important points. We'll come up with some kind of table. And based on that table, or we can say array, and that array will tell us the stability of the system. And the way we follow, the process we follow that array actually called Routh stability criterion methods. From that array, we can come up with some kind of comments that system is stable or not. So the way we'll be solving in this method, in this approach, is called Routh stability criterion. So this is, if I say it is better, I can say Routh stability criterion. So in this part, two important points: the Routh stability criterion tells us whether or not there are unstable roots of characteristic equation exists in the positive real axis without solving for them. So from this stability criterion, we can come up with the conclusion whether the system's poles are in the right-hand side or not. So as you know, if any poles comes in the first half, so this is our one half, This is another half. So here, if the poles exist in this region, then we generally call the system is unstable. And if they are in this region, the system are stable. So from the route stability criteria, we can say any poles exist on the right-hand side or not. And also we can come up with the gains in the system. If based on the gains, we can comment for these gains, the system will be stable and unstable. We can come up with some conclusion. So let's go to the another point. The range of BI also can be guaranteed for stability. What does it mean? Because if you compare both this equation and this equation, suppose equation number 1 and equation number 2. So here B1, B0, these are what? This is, you can say these are in this B1, B2, B3 or till Bn, the controller gain may exist. So based on these gains also we can comment on the stability for the range of this coefficient. So let's go with the condition. The coefficient B1, B2, Bn must be positive if any of them are negative or zero, a pole exists either on the imaginary axis or has a positive real part. For the stability, all the values of all these coefficient B1, B2 till Bn should be positive. Yeah, any of the four, I mean, these values are comes with negative or zero, then it is quite confident that the system is going to the unstable. Now, another condition is, this is the first condition. Second condition, if Bi is greater than zero, that the first condition, if it is fulfilled, if all are positive, we can form a route array. So let's look how the route array looks like. So we'll take Sn, Sn minus 1, n minus 2, S2, S1, and S0. So we'll start with, if it is n is odd, we'll take the coefficient of odd Ss. If n is even, if the, for example, in this case, if n is even, then we'll take the even value of Ss coefficient. Let me write B0, for example, B2, this is even number, B4, B6, irregular. And for the, if it is even, then we'll go to odd, B1, B3, B5, B7. We'll come up with the example, then it will be clear to you. And based on these two rows, we can form the rest of the rows. So let's go C1, for example, C2 are the terms coming out from the first two rows, C3, C4. Let's assume this F1, F2, Z1, H1. So how we can, because first two row we can form from the given characteristic equation, but rest of the rows how you are forming. Let's write here where C1 is actually this into this minus this into this divided by B1. And C2 will be B1 into B4 minus B0 into B5 divided by B1. C3 will be B1 into B6, B0 into B7 divided by B1. So let me write B1, B2 minus B3, B0 divided by B1. And C2, B1, B4 minus B5, B0 divided by B1. And C3, B1, B0 minus B7, B0 divided by B1. So this is how we'll form the rest of the rows. Let me write this process will continue until the nth row has been completed. Once the route array has been constructed, asymptotic stability can be determined by first column of the coefficient. So what does it mean? So after forming this route array, we will check the first column, the coefficient, the terms in the first column. And if all the terms are positive, then we can say the system is asymptotically stable. If any of the terms comes out to be negative, then it will be ensured that the system will be unstable. There are poles exist on the right hand side. So let me write the closed loop. The closed loop transfer function is asymptotically stable if and only if all the coefficient in the first column are positive. Let's take an example, then this problem will be clear. Let's take a simple example. Let's assume we have a characteristic equation s to the 4 from the closed loop transfer function 2s3 plus 3s square plus 4s plus 5 equal to 0. This is the characteristic equation we are getting from closed loop transfer function. And we can form the route array. So there's the highest power of S is 4. So we'll start with the even, then we'll start with odd. So S4, S3, S2, S1, and S0. So from the even coefficient, we can write 1, 3, 5. This is coefficient of S4 is 1, this is 3, and 5. And odd to be 2, 2, 4, and not 0. Now we'll use the concept we have done here, this concept. So we'll B1, B2 for the first. So we'll multiply 2 into 3 minus 1 into 4 divided by 2. So it comes out to be 1, 5, and you can form this array minus 3. Same approach you can follow. So what is we are having in the first column? We can see there is a sign change here, minus 3. So there are actually two sign change. If you notice, 1 to minus 3 and minus 3 to again 5. So there is two sign change. We can write here the number of sign change. Based on the number of sign change, we can say number of poles exist on the right hand side. Number of sign changes in the first column is 2. Hence, there are 2 poles or roots of characteristic equation exist in the positive real axis. So this is how we can comment on the stability. So it means the system is unstable. 2 roots are there in the positive half. Let's take another example where we'll find the range of gain in the system so that system will be stable. So let's take another example. Let's consider the following example, following block diagram. We are having summing point here, R of S, and we are having the transfer function which includes the transplant and controller. Ky s into s square plus s plus 1 and s plus 2, and output is y, and the feedback, this is negative, this is positive. So this is the some system. So here the question is determine the range of k for which the system stability is ensured. So it means we have to find the first route array, and we will check the first column, and based on which we will find the value of k for which the first column will be always positive, all the terms in the first column. So solution, the closed loop transfer function, we can come up ys divided by rs equal to k upon s into s plus s, s square plus s plus 1, s plus 2 plus k. And the characteristic equation from this we can write from the denominator part, s to the 4 plus 3s cube plus 3s square plus 2s plus k equal to 0. So route array we can form, s to the 4, s to the 3, s square, s1, s0. So from the even SS, we can form the row 1, 3, and k. And from the odd coefficient, we can have 3, 2, 0. So here 7 by 3. 3 into 3 minus 2 into 1, so 7 by 3. And here it is k. And for S1, 2 minus 9 by 7, k. So it's k here. So for stability, as you know, the first column should be, all the terms in the first column should be positive. So based on this condition, we can come up for stability. Stability, we can write 2 minus 9 by 7 k should be greater than 0. And from which we can come up k should be less than 14 by 9. And from which we can come up with the condition for stability k. So in this case, k should be 0. So I can write 0 greater than k and less than 14 by 9. So this is the range of k for which the system will be stable. So this is kind of the gain tuning, how we can come up with some gain value for which the overall closed loop system will be stable. So this is very, simple way to find the gain range for which the system will be stable. If you choose the controller gain in this range, the system will be stable. Now let's go with another example. This is a little complicated example. Let's work on it. Consider the following characteristic equation of a closed loop system. X to the 5 plus 4 s to the 4, 4 s to the 4 plus 8 s to the cube plus 8 s square plus 7s plus 4 equal to 0. So this is the characteristic equation we are having from a closed loop system, and we will discuss stability on this system. But first we have to do the Routh array. So we'll start from s to the 5, s to the 4, s to the 3, s to the square, s1 and s0. And for the odd values, we can come up with 1, 8, 7. For the even, 4, 8, 4. And the rest of the rows can be filled as 0, 6, 6, 0, 4, 4, 0, and 0, 0. So this is one of the critical case. If 0, 0 comes into the in any of the rows, so what will happen? So let's work on this. Let me write, because of row of zeros appears prematurely, we form a auxiliary equation using coefficient of s to the power 2 row. This is very, very important. If any of the row comes out to be 0, then we will choose the previous row and we'll form a auxiliary equation from the previous row. So here in this row, we are having 0. So we'll choose this row as the auxiliary equation. So let's write. So auxiliary equation is, we can write 4s square plus 4. This is basically even equation equal to 0. And we'll take the derivative of s with respect to s. So the derivative of s with respect to s, which yields dAs by ds equal to 8s plus 0. We can write. So equal to 0. So now from which we can come up with the coefficient basically 8 and 0. If you, this is, so now what we'll do is this equation coefficient will fill with s to the power a 1 row. So what we'll do is 8 and 0 will replace zeros in S1 row. S1 row of the original array. So then we can write, let's start with S1 where 8 and 0 and S0 will be 4. So if you substitute in this row 8 and 0, so S0 row will be 4. So this is basically we can write coefficient of S by ds. So now we'll have some more treatment on this equation, particular equation. This is very important. So let's go. So here, if any of the row array, 0th row is coming, in any of the row, all the terms, all the elements are 0, then it is quite confident that you'll be confident that there is poles exist on the imaginary axis of the closed loop system. So let me write. There are solving equation. Let me write. This is the equation number 1, and this is equation number 2. Solving equation number 1, we get two roots, which are basically at s equal to j and s equal to minus j, which are also two of the roots of characteristic equation. Very, very important. So if you solve this equation, we are having two roots which are complex conjugate, and these roots also the root of this our main characteristic equation. Thus we can write, hence the characteristic equation has two roots on the j omega axis, and we can solve the marginal value of system parameter for system stability. So it means we can if there is some unknown a coefficient exists in the system, and we can come up with the condition of that unknown coefficient, the system will be marginally stable or fully stable or unstable. So this is the way we can also find the gain of the system, because in the previous example, if you notice, if for example k equal to 14 by 9, if it is like that, or if it is k equal to, for example, so yeah, 14 by 9, if you choose this case, then there'll be 0. 0th row will come, and due to that, the system will be marginally stable. So that's why we can find the range of K on which the system will be stable. So this is very, very important method to find the values of controller gain for stability. What are the range of the controller gains? For that range, we can comment that system will be stable. Outside the range, the system will be unstable. So this is how we can check the stability of the system of a closed loop system transfer function. So let's stop it here. We'll continue from the next lecture on new topic. Thank you.